So in our previous video, we left you with a cliffhanger, how we're going to prove that this actually converges or diverges. And unfortunately, when we tried to use the direct comparison test, it didn't work. So what else is there? Well, fortunately for us, there's the limit comparison test. So this one didn't work. That's okay. Let's take a look at the direct comparison test, or excuse me, the limit comparison test. And basically this says, if you have a series, if you have two series with positive terms, and the limit of the ratio of those terms is some constant, basically it's some constant that's greater than zero and finite, then what one series does, the other one does. So if one series converges, so does the other one. If one series diverges, so does the other one. They both have the same behavior, is what it's saying. And this is a beautiful test. In fact, I would recommend that you not use the direct comparison test at all. I mean, I do mention it because, you know, occasionally it can be helpful. But the thing about the direct comparison test is that students often get the inequality messed up, and they prove something with the wrong series, or they prove something they can't. With the limit comparison test, there's no problem. In fact, when we were looking at the direct comparison test, we wanted to use 1 over k cubed, but we couldn't because the inequality runs in the wrong direction. But with the limit comparison test, we can. So I'll call that my b sub k. This is my a sub k. In order to show convergence or divergence, I'm going to look at the limit as k approaches infinity of a sub k over b sub k. And if that limit is a nice finite constant, I'll be done. Because we know something about this series, right? What can you tell me about this series? Nothing? Come on, make me look good. What do you know about?
Converges.
Converges. Why does it converge?
Because it's greater than 1, p equals 3.
Yeah, p series and p equals 3. So it converges. Great. So let's calculate this limit then. That's going to be the limit as k approaches infinity of 1 over k cubed minus 5 over 1 over k cubed. When you divide by a fraction, it's equivalent to multiplying by the reciprocal, so it's the limit as k approaches infinity of 1 over k cubed minus 5 times k cubed over 1. Now you could, I suppose, if you wanted to, use L'Hopital's rule here. K approaches infinity, k cubed over k cubed minus 5. But I'm hoping we don't have to, because you'd have to use L'Hopital's rule a total of 3 times, really. Can anyone tell me what that limit is?
1.
It's 1. Good. How'd you get it so fast?
P and Q are the same, so you take the ratio of the coefficients.
Perfect. So the leading coefficient of your highest degree term is 1 in both cases. And when the degrees here match, then the limit is just the ratio of those two leading coefficients. In this case, it's 1. Now, because this is finite, then this series converges by the direct or by the limit comparison test. So therefore, the summation k equals 1 to infinity of 1 over k cubed minus 5 converges by the limit comparison test, the LCT. Nice. I like this because It doesn't rely on you sitting there and hemming and hawing, going, do I need it greater than or do I need it less than, etc. It's nice. The one thing you got to be careful of is that your limit isn't zero. If it's zero or infinity, you got to choose a different series. This has to be strictly some finite number in order for the limit comparison test to apply.
Why'd you put the less than infinity next to it?
Oh, just because, like I said, with this test, the result has to be, all right, so our result C has to be a finite number. So basically all I was saying is that, okay, C is a finite number. It's less than infinity, right? 1 is less than infinity. So that's why I put it there. I didn't need to. I just did. Okay. Anything else on that one? All right. Let's take a look at a couple more examples.
If it was divergent, you just put divergent, that's it.
Yeah, so yeah, we just put divergent. And let's take a look at, let's see, you can call it example F. Sum from n equals 1 to infinity of n plus 7 over n times the square root of n. Well, like I said, I'm not a big fan of messing around with the limit or with the direct comparison test, because then you got to really sit there and think, you know, greater than, less than. And look, it gets confusing. People make mistakes with it all the time. A surer bet is to try and use the limit comparison test. And for that, what I do is I look at this and say, all right, let's just take a look at n over n times square root of n is n to what power?
1/2.
1/2. And guess what? Those cancel. So 1 over n to the 1/2. What if I chose that for my b sub n? This is my a sub n. What's your guess based on what you know about this series? A series composed of these terms is going to do what?
Diverge.
Diverge. So I'm guessing that that's what we're going to conclude about this one. We'll see. Thanks, Nora. Limit as n approaches infinity of a sub n over b sub n. So that's going to be the limit as n approaches infinity of n plus 7 n divided by square root of n times, well, dividing by a fraction is like multiplying by the reciprocal. So let me just multiply by square root of n over 1. And I'm going to get some nice cancellation. So the square roots cancel. And really, I'm left with limit as n approaches infinity of n plus 7 over n.
This will be infinity over infinity.
All right, it is infinity over infinity, but there's two things you can do to get the conclusion. One is you can use the big bazooka, which would be L'Hopital's rule, which is what you're saying, and that's fine. But suppose you didn't want to work that hard. What's the other way to do this?
Powers are the same.
Yeah, the powers.
Powers are the same, so it's a ratio of the leading coefficients. So 1 over 1 or just 1. Now, since this is divergent p-series, then we could say, therefore, this series n plus 7 over n squareds of n diverges by the limit comparison test. Nice.
So why did we solve to get 1?
Oh, well, you have to calculate this limit and make sure that you get a finite number.
Gotcha.
That's all that matters. Now, this could end up could have been 10, could have been a million, could have been a billion, but as long as it's finite and greater than 0, that's all that matters. So, you know, it's just a habit of mine somehow or another that a lot of my limits will turn into 1. But you know what? You know, if you wanted here, Nash, you could have put maybe a 12 up here in the numerator, and that'd be a 12 here, and then I'd end up with 1/12. But you know what? 1/12 is telling you the same thing that 1 is. Because it's greater than 0 and less than infinity, then this would diverge because of the limit comparison test. It just has to be finite. It has to be 0 less than c less than infinity. So whatever your limit is, as long as it fits in between here, then the limit comparison test applies. If you get a 0 or if you get an infinity, go back and choose a different series for your comparison.
What if we get negative?
You shouldn't, because in order to do this, your series have to be positive terms. So if you look back here, yeah, positive terms.
In other words, if you get a negative, you messed up.
That'd be a good conclusion. Yeah, if you got a negative, then go back and fix it because you did something wrong. Yeah, I'd be very happy to see. Oh wait, you know, did something wrong. So that'd be some nice critical thinking. Hey, that's management potential there, Nash. Just saying. Okay. Let's do a couple more. Example G. So we'll do the sum of n equals 1 to infinity of 5 to the n over 14 plus 8 to the n. Okay. So this term, you know, the 14 here, like I've said before, these finite terms, these terms that don't involve n, are going to kind of get drowned out when you start looking at large and large values for n. I mean, for instance, 8 cubed is what, 512. 8 to the 4th power is already 4,096. Wow. Powers of 8 get really big really fast. And that 14 is eventually not going to mean much. So that's kind of putting my mind into thinking b sub n would be 5 to the n over 8 to the n. Or I could also write it as 5 over 8 to the n. And I only write it this way, not from a calculation standpoint, but for you to think about it in terms of a series. And we know this series. We discussed it earlier today. 5 over 8 to the n. What would the terms in this series look like? 5 over 8 plus 25 over 64 plus 125 over 512, and so on. But what do you know about this series? What can you tell me that we learned today?
Geometric?
Yeah. Oh, awesome. Awesome. I thought I was going to have to give out some extra credit. Cool. Thank you.
Take it.
Yeah. You'll take it anyways? All right. Yeah, it's geometric. with r equal 5/8. And if r equals 5/8, what's that telling me about my my series? It converges. Remember, because the absolute value is less than 1. So great. So I know that this is a convergent series. That's making me think that this is probably a convergent series too. We just got to check it. And we'll check it with the limit comparison test. So we'll call that my a sub n. We'll calculate the limit as n approaches infinity of, let's see, be 5 to the n over 14 plus 8 to the n divided by b sub n is like multiplying by the reciprocal of b sub n. Like that. Boy, it's kind of an ugly limit calculation. Oh, well, we can make our life a little simpler right away, right? Those two cancel. Duh. What was I thinking? Limit as n approaches infinity of 8 to the n over 14 plus 8 to the n. That one might not be as clear. But if you wanted to make it a little bit more clear, here's what you could do. You could multiply both the numerator and denominator by the same thing, 1 over 8 to the n. What does that do for me? That gives me the limit as n approaches infinity. If I distribute this here, I get 1. And here in the denominator, I also get a 1. And here I get 14 over 8 to the n. Does that help me? Actually, yes. Because when I calculate this limit, in the numerator, I get 1. In the denominator, I get 0 plus 1. Overall, I get a limit of 1. Now, if I got a finite limit, therefore, by the LCT, limit comparison test, this one converges. Beautiful. Any thoughts on G there? Now, at various points on exam, I might ask you for what tests are possible. What tests would you consider? Certainly the direct comparison test is something that you can list, but I really don't expect people to use the direct comparison test much. In fact, most of your homework problems, I would suggest use other tests, integral tests, limit comparison tests, geometric series tests, telescoping series. This is not exactly a test, but it is a way to find these limits. Okay. Last one. Let's take a look at this series. The sum from n equals 1 to infinity of 17 over 1 plus 2 to the n. I'll call that S. First of all, what do you think? Do you think this series is going to be convergent or divergent? At a guess.
Divergence.
Diverges? Okay.
Both.
Now, in this particular case, I'd probably use something close to this. In fact, Nash, you were asking earlier, I mean, you're always coming out the one. What if I just looked at the important part here in this? And then I said, all right, let's let B sub n equal 1 over 2 to the n. Okay, I can do that. And use that as my limit comparison test, because I know that this sum, n equals 1 to infinity of 1 over 2 to the n, that's going to be a convergent, don't say P series, it's convergent geometric series.
Is that because P is not over 1 or greater than 1?
Well, we don't really have a P here. This isn't fixed, right?
Gotcha.
So that's the difference here. So if you were to look at that series, that's like the one I made the joke about earlier, that infinite number of mathematicians. You'd have 1 plus 1/2 plus 1/4 plus 1/8 and so on. So it's a convergent geometric series, R equals 1/2. Now, if you took a look at the limit as n approaches infinity of, calling that a sub n over b sub n, that would be the limit as n approaches infinity of this divided by b sub n. It's really going to be this times the reciprocal of this, 17 over 1 plus 2 to the n times 2 to the n over 1. And interestingly enough, in this case, because of the way we chose b sub n, can anyone tell me what we're going to end up with? You can kind of bring the 17 out in front. What you'll be left with is 2 to the n over 1 plus 2 to the n.
So it should just be 1.
Yeah. So I'll end up with 17 times 1, or 17. And the important thing is that it's finite. It's less than infinity. So therefore, the series converges. 17 over 1 plus 2 to the n converges by the LCT. Now, this problem in the book asks you to do a little bit more. In the book, or excuse me, not in the book, but in WebAssign, they ask you to use the first 10 terms to approximate the series. And then we'll see if we can't come up with a remainder term as well. So S sub 10 would be the sum from n equals 1 to 10 of 17 over 1 plus 2 to the n. That's not something that I suggest that you do by hand. I hope you embrace some technology. Can I get away with doing this here, or do you want me to do it on the software? All right. I'll just do it here so I can bang it out kind of quick. Hit the second key, then the list key. Go over to math. The fifth option down is sum. And then we need to sum up the list of the first 10 of these. So I'm going to go back to the same menu, second, and then stat. This time go over to ops. It's again the fifth one down, gives me a sequence, gives me a nice menu-driven way to enter in this expression. So I'll clear that out, type in 17 divided by parentheses 1 plus 2 to the n, in this case 2 to the x, close parenthesis. The variable that you're summing is x, start at 1, go to 10. All that looks good. When I press enter down at the bottom, it's going to paste that in. And I'll take the sum of all those. Let's put in a right parenthesis just for good measure. 12.799001. All right, so that's the approximation with the first 10. They ask you to go a little farther and estimate the error. Now, in estimating the error, they do something a little different on this one that they've done with the previous ones. So you might want to pay attention to this so you get that last little point off of this problem. I think it's the last problem in your homework. But what they notice is that 17 over 1 plus 2 to the n is less than 17 over 2 to the n. Why is that important? I mean, it's a nice observation, but why is that important? It's important because this is a geometric series. And we can sum that one up. But what we're going to do is we're going to sum it up not from 1 to infinity, but from the first term we left off, which is 11. So the error is going to be approximately, it's going to be less than, really, the sum from n equals 11 to infinity of 17 over 2 to the n. And that's still a geometric series. If you look at the first term is when you plug in an n equals 11. I have 17 over 2 to the 11th plus 17 over 2 to the 12th. It's still a geometric series with r equal 1/2. That's your first term. So the sum of this is going to be a sub 1 over 1 minus r, which is going to be 17 over 2 to the 11th divided by 1 minus 1/2. And basically, this is going to be dividing by 1/2 or multiplying by 2. Multiplying by 2 is going to cancel one of the 2's there. 17 over 2 to the 10th. You can get a decimal value for that off your calculator. It's about 0.0166. So that'd be the approximate error in using just the first 10 terms of this series to approximate the overall total. All right. Give yourself a pat on the back for still being here. Good on you. Questions on this last one? I mean, I doubt I'm going to get any this late in the day, but I'll throw it out there anyways. Anything for the good of the order. All right. Well, let's stop here.